Okay, good morning. I'm Changhoon Kim. I go by Chang or Chang Kim. Today I represent P4 Language Consortium, but I also work for Barefoot Networks. The main topic that I'm going to talk about today is data plane program mobility, and this is going to introduce a lot of big shift in the way people build and manage and operate their networks. So let me quickly go through some of the key points here. So suppose you're building a networking system. Your switch will typically have something like this. It has switch operating system, a variant of Linux operating system. In the user space, you have some applications, routing protocol daemons such as OSPF, BGP, and so on. And then there is a simple layer called switch chip driver, which connects the operating system to the actual hardware chip. Now, imagine that you wanted to introduce a very important feature for your business, such as VXLAN. Imagine that you were at like 2010. VXLAN, network virtualization protocols, NVGRE, those things were just being invented. And then you really wanted to introduce these technologies in your network, data center carriers, as quickly as possible. Do you remember how long it took for us to get these kind of features? It took 4 years, really. And then the reason is that this VXLAN applications, driver changes, those things are all software. But the hardware chip itself actually needs to handle VXLAN frames differently. It handles packet processing differently. It has to parse different fields. So it needed some hardware changes. And then really it took 4 years. And then interesting thing here is that this is not a low priority simple feature or some monitoring feature. This is one of the most important critical business-centric features, and yet it took 4 years. Why? Why did it take so long? So if you're a network owner, you will first tell that, hey, I need these and these features to your network equipment vendors. And then the vendors will start to socialize these ideas by going to ITF, IEEE, or by meeting with the other vendors. And then internally, they decided, okay, this needs this kind of software changes. So they deliver this to their software division, and then software division typically will say that, yeah, give me a few weeks or a few months, I can deliver this. When you go to your ASIC team, however, they will say that, give me 3 years. And that's the reality of building any new, modern day silicon. And therefore, you also hear years, 3 years, 4 years, okay? So, and unfortunately today, so you can't just get a new feature because equipment vendor cannot just send out new software patches or upgrades. And new forwarding features take years to develop. And by the time you have secured the solutions, you probably have come up with some kludgy way of getting around the problems, and your network have gotten even more complicated. And eventually, when the upgrade is finally available in 3-4 years, you realize that you kind of worked around the problem, or the solution is actually not exactly what I wanted originally, like 4 years ago. And even if it actually turned out to be working, you have to forklift your entire network, causing you another year or 2 years of upgrade time. So, and key reason why this is happening is because network systems are today built entirely bottoms up. There is this thing called fixed function switching chips running at multi-tera BPS, and then somehow the system builders figure out how these chips work. Even if these chips were developed in-house, in your own company, you have to read, hundreds or thousands of pages of register, use cases or data specifications. And then you have to figure out that, oh yeah, if I configure this register, if I call this SDKs, it'll do this way. But if I give slightly different parameters, it'll do something different. So you have to understand those kind of complicated things and then build your system. Our goal is entirely changing this. We want to make this entirely top-down approach where you as a network owner, network device owner, just tell that, hey, this is precisely how your device should process these packets. And then you describe it not in human language, but in a machine language such as P4, and then you program it. So this becomes your own switch running your own programs. Okay? So obviously the question is, why hasn't this happened so far? Why are old network systems already built this way? And the conventional wisdom is that programmable switches are going to be, an order or 2 orders of magnitude slower, and then more expensive, and then more power hungry than any fixed function chips. That was true. That had been true for decades. Now, one of the most important things that is happening in the industry right now is that this is not anymore true. This is going away. And then we're actually observing a few evidences. First, for example, Barefoot has released this 6.5 terabps fully programmable packet switching solution last year. A few other companies working in this field, such as Broadcom, Cavium, have released programmable solutions running at slightly lower speed or sometimes a little less programmability, but still they're delivering similar kind of solutions now, right? And this solution, for example, is actually the fastest working chip out there, and then it is fully programmable. And then we call this a PISA architecture, protocol independent switch architecture. And Topino just happens to be one incarnation of such architecture. And we're expecting to see many, many more different types of incarnations. So one quick question is, why now then? Why hasn't this happened before? And maybe I can give another 15, 20 minutes talk to talk about only the technical aspect of this one. But the summary here is this one. The entire computing industry has observed this pattern many times. For example, 4 decades ago, computers became generally programmable targets, right? Nobody writes their own applications in hardware, in CPU anymore. It's like, our father's generation. So those kind of problems, and then we're not living in that world. Graphics card, maybe 20 years ago, until GPGPUs come up, we're actually implementing hard-coded graphics algorithms in hardware. Once GPGPU came up, it quickly became, the dominant type of chip, and it is actually the fastest chip. Nobody even think about going back to the programmable era. Signal processing, exactly the same thing happened in the DSP world. Machine learning field, this is right now happening, right? Instead of using CPUs, people have realized that, there is a repeated instruction set here. We can build something like TensorFlow chips. And what about networking, right? So eventually it's bound to happen, and then we believe that the time is mature for this. And then in the case of networking, that domain-specific language that we're using is probably going to be P4. And then we'll have this P4 compiler that translates P4 programs into the specifications or configurations of the programmable chips, the PISA incarnations. So this language needs to be sort of nurtured in a sort of communal way. That's why we built this language consortium called p4.org. It's entirely open source organization based on Apache 2 license. The original P4 ideas came from Google, Microsoft, Princeton, Stanford, and Barefoot, and Intel. They're all members, of course, but there are many other members and players here. For example, there are many operators, service providers, system builders, target builders, the packet processor builders with different tiers, like high-speed ASIC to NPU or FPGA-based solution providers, or even CPU-based solution providers as well. And then other integration and solution service providers, and of course academia and research people. So in summary, PISA, the protocol independent switch architecture, and P4 together deliver the highest performance that you have seen, as well as fully programmable flexibility, and then it doesn't cost you any. It's merchant, roughly running at the same speed and power budget as any fixed function chips, and it's this abstraction, domain-specific abstraction that P4 offers is very simple and very intuitive, especially for network engineers. So in fact, some of the one of the P4 contributors at the language consortium, once they learned how to use some open source code, they started making contributions back within 24 hours. Right? So that's the kind of speed and velocity that we're talking about with these domain-specific abstractions and programmable targets. So how is P4 programmability then used? At the end of the day, we all want to see some cool new things that are enabled by these new technologies. So what are those? So there are maybe a few things, but I just wanted to talk about 4 important things here today. So the first thing is actually reducing complexity. So for example, when you build your own switch, you can use the reference P4 program called switch.p4. This is the open source version of switch data plane implementation. It actually implements lots of existing features. I mean, of course, I won't go through this list, but this is almost comparable to fixed function chips, and this is about 7,000 lines of P4 code. So that abstraction is actually very powerful. But if you think about your own particular environment, you don't necessarily need to use all these features. You can actually scratch up a lot of things. For example, if you're building a very simple data center side network, essentially what you need is just IPv4, v6, ECMP, lag, echo. That's all. All the rest can actually go away, and then once you remove them, you can actually use the entire silicon, SRAM, logic, TCAM for exactly your own feature set. So you can actually increase your table significantly. So that's the customization, the power of customization. For example here, if you are willing to customize this reference implementation switch.p4 and then compare that result with the existing, say, 3.2 fixed function chips, you can improve table sizes sometimes by more than 2 orders of magnitude over their IPv4 host route examples. Okay. The second use case is adding proprietary features. Okay, you can simplify it, but you can also customize your own network. And 30 years ago, maybe this was the network feature that you wanted. Today, if you actually visualize that reference switch.p4, it's almost not readable on this kind of screen. You have to magnify only a section, and then that single section looks like this one. So this huge set of features are now added, and you can actually, this actually means that there's a lot of demand for customization, right? And what we have seen so far, based on the interactions that we had with partners and potential customers or contributors, people want to introduce their own new encapsulations and tunnels, new ways to tag packets for special treatment. This is particularly useful in the context of NFV because you can attach some information between the NFV boxes and then offload a lot of information down to the switches. New approaches to routing. For example, large data centers really want to do source routing. New approaches to congestion control, new ways to process packets. For example, high-frequency traders, financial firms really want to split packets based on the contents, like ticker symbols, stock symbols, and then use different paths for to reduce networking latencies and so on. We have also observed a lot of cool new applications, such as world's fastest layer 4 connection load balancer. The lower half of the connection load balancing functionality can actually be folded into the switches, and now once it's folded into the switches, it runs at full line rate that the switch supports. Say it's 3.2 terabps, 6.4 terabps. So this is at least an order of magnitude faster box, and then at least an order of magnitude cheaper box compared to existing ones. World's fastest stateless firewalls are also frequently mentioned. The third use case is silicon independence. So one very important aspect of using machine language here is that when you define your own P4 program for your switches, and when you compile it, it actually auto-generates the API through which you can configure the switches at runtime. So if you introduce your own tables, you need to add entries, delete entries, modified entries at the runtime through your networking applications, right? So that the API that those applications use are now auto-generated. What that means is that as long as you use the same P4 program, you own the SDK, right? So, and when you actually go to the next generations of the chips or even different chips in the same generation, as long as you use the same P4 program, you don't need to change your control plane at all. Right? So that benefit is actually huge, and that's why Google and Barefoot decide to jointly invest in this direction and then contribute these results back to the language consortium. Okay. So this just indicates that this the channel between the logically centralized control plane and the individual devices, the implementation of this is actually auto-generated by the compiler. The last one is network telemetry. So this network telemetry is almost a step or poster child of this data plane programmability now. So let me talk about a few simple things, but very powerful things here. Suppose you have your own network, and then packets are, traveling here and there. What you exactly want to do is asking these 4 questions to your network solutions or network equipment. Pick any packet in your network, and then ask this question: which path did you take? Okay, and you want an answer like this one. I'm packet A, I visited switch X, Y, and Z at this time. Second question, why did you take that path? Why did you come here instead of going to other path? Right? That's mainly dictated by the table entries that are used for the packets. So I want to collect which rules did my packet actually follow. The third question is about latency. How long did you take to come here from your source? Okay, and in typical data center like or enterprise like environment, propagation latency is negligible. So most latency is almost always switch queuing latency. If it's a service carrier environment, then propagation latency can matter. In that case, knowing about the path can also give you the latency or the explanations behind the latency as well. Okay, and then the fourth question, so the answer that you're expecting from the third question is like this nanosecond numbers, right? First 2 switches look fine, but somehow at the third switch, I spend like 20 milliseconds. Okay, then of course the next question is why? Okay, why did you end up spending that much time, 2 orders of magnitude more time in that switch? And that, to answer that, you need to ask this kind of question: which other packets were there when you were waiting there in that queue? Okay, because the other packets which cause this kind of latency increase are probably the culprit of this queuing delay. Okay, so in this particular case, for example, there was an aggressor flow which, for example, is not TCP, a UDP, bursty flow that happens to be sharing the same output queue with this green flow that causes a lot of damage to the green flow's performance. And if you look at the queue occupancy and the composition of the queue at that time, you can see that, oh, this orange guy is taking most of the queue. Okay, so I have to throttle it or I have to kick it away. So these 4 key questions, I mean, it's so natural that if you have your own networks, you want to ask these kind of questions and then get the answers, right? And you couldn't do that with existing devices because you didn't have programmability, or if you had programmability, you had to compromise your performance. Now with PISA and P4, you don't need to compromise. You can introduce your own monitoring logic without worrying about, higher cost or power budget. Okay? So one such example is what we call INT. This is again, open source technology through P4 Language Consortium. What you can do is this one. So when your network devices deliver the packets, they actually use the regular packets as log packets. So the first packet arrives at the first switch. The first switch adds its own metadata, like I'm switch X, it arrived at switch port ID X, it was forwarded out to Y, and the queuing latency this packet has observed is blah, blah, nanosecond. The next switch can add its own information. Every switch can do the same thing, and then when the switch arrives at the packet arrives at the last stop, you can just undo the changes, but you can collect this, metadata stack. So now you essentially used regular packets as log packets, and your applications continue to work fine because you didn't change the original packets. You actually undid all these changes that you made. And then you can visualize, analyze, use this for later analysis. So this is such a powerful mechanism. So I just wanted to show you a very quick demo video and then conclude my talk here. So for example, you have a cloud fabric network and then one top-of-rack switch here at the bottom, and then one, say, smart NIC or virtual switch environment connecting between the 2 VMs to the physical network. Sometimes when you do some NFV applications, these packets go through the VMs multiple times, right? And then sometimes you observe latency, significant latency. You want to know whether it's actually physical switch or the smart NIC or the virtual switch, the VMs, if the VMs, which VM. You want to know about them for every single packet. And now you can do that because you can use these technologies like in-band network telemetry. So let me show you this final demo. So we have built exactly the 2 VM environment, and then we're collecting per packet latency information, and then we're showing the end-to-end latency each packet is observing in this time series, somewhere between 0 to a few, is it millisecond? Okay. Interesting thing is that for every single packet now we actually get the actual breakdown of the latency. And then different colors mean different components here. So, and you can easily see here that the vast majority of latency are caused by the VMs, because VMs are running some software applications, and physical NICs and virtual switches or smart NICs are fast enough here, fortunately. Okay, and if you go a little further down, you can actually observe that for every single packet, we have collected the exact latency at the granularity of nanoseconds. So if sometimes physical switches go bad, you can tell that, oh, it went bad at this time. These packets or these flows are exactly affected, and then here is the root cause. Okay, so this kind of detailed visibility is really powerful, and going to open a lot of exciting use cases and applications. And that concludes my talk. Okay, thank you very much.